All right, hello there. So we're starting a new chapter with this video. This is chapter 4. And in chapter 4, and today, what I'm going to do for you is I'm going to introduce a new idea. And that idea is the idea of a moment. Okay. Now, a moment is the rotational equivalent of a force. A force tries to push something or to pull something. What a moment does is it tries to twist something. Okay. We could say that a force tries to change um, the translational acceleration of an object, make it go faster or slower, change its direction, whereas a moment tries to change the angular acceleration of an object. So if it's spinning, stop it from spinning, slow it down, speed it up, or if it's not spinning, make it spin. All right. Now, this is dynamics. Sorry, this is not dynamics. This is statics. So we're not interested in accelerations. We'll do that in the spring. But for now, what we're doing is we're trying to think about basically something like this. We've got this force, and it's going to try to twist the little L-shaped structure there. Okay. And what we want to know is if we could put a pin at O. So we put a pin right here. What is that twisting effort? Okay. How much is that twisting effort? And in what direction is it? Okay. So there's three different ways to go about this. And I'm going to show you all three of them here with this. You need to know all three of them. So try not to be like, oh, well, I'll just do that every time. It'll be fine. Okay, don't do that because you need all three of these. If you just limit yourself to one, that's like saying, hey, I'm only ever going to use a flathead screwdriver. All right, that's going to get the job done often, but it's not always going to get the job done. So put more tools in your toolbox. So we begin with really the basic way to think about the moment, which is to say that by definition, a moment happens to be what we call the moment arm, which is a distance, crossed with the force vector of interest. Okay. So obviously, this guy up here is F. And I'm going to go ahead and put it into its um, components. And it goes as 4/5 and 3/5. So the x component is 4/5. So it's 4/5 times 100. So that becomes 80. And the y component is 3/5 times 100, which is 60, but it's negative. So I've got minus 60 in here. And then the x component of that force is 0. Okay. Okay, let me make that just a little bit smaller. I got a lot of stuff to put on the page today. Um, okay, I'll do it in two pieces like this. I'll just sort of scoot it out of the way. Now, there's F, and then my moment arm is the distance from the point of interest for rotational purposes, for twisting purposes, which it tells us is O. And so that is our right there. Okay. And our vector in this case is pretty easy. We just are going to go over 5 in x, and we're going to go up 2 in y. So we have this relationship right here. Okay. And let me move that because it's obscured by my picture. Wow. Okay. Didn't want that to happen. Okay. Moving my picture, I guess. I'll go over here. There we go. I'll switch sides. If I do this, does it look like I'm looking at the equation? Look at that equation. That is awesome. All right. So there's my R and there's my F. And so the first method I want to show you is we're simply going to use R and F, and we're going to say that our moment is going to be the vector r, which we said was 5, 2, 0, or 5, 2, not, if you've been watching any videos that from British people. But we got 5, 2, 0, and we're going to cross that with 80 minus 60, 0. Okay. So I'm going to do this old school. We'll do it by hand. And then I'll have a suggestion for you. So we use the determinate method to do this. So I've got I, J, and K here. And then the first line I put in the first vector, which is R. So I'm going to put in 5, 2, 0. And then the second line, I'm going to put in the force vector F because it's R crossed F. So it's the first one across the second one. So I've got 80 minus 60 onto 0. Okay, so when I get ready to do this, I'm going to have I on 2. Then I'm going to do those two parts. 2 times 0 minus 60 times 0, which gets me a 0 minus 0. Okay. And I need a different color to do that in. I'm sorry. This is going to bug me. So I'm going to go this minus this. Okay. Just like that. And then, anyway, I still get 0 minus 0. Then make sure you put minus j. Okay. And now this time we're going to do this times this minus this times this. But no matter which way we slice it, we're still going to end up with 0 minus 0 on that one. And then we have plus k. And this time we're going to have this times this minus this times this. Okay. So that gives us minus 300 minus 140. Okay. And so what I'm going to end up getting for m is that m is going to have to be the vector 0, 0, minus 440. Okay. Minus 4. Oh, I'm sorry. It's that's not right. It's 460. That's a 160 right there. Okay. Sorry for the typo there. Okay. So that's my moment by definition. And it's a three-dimensional vector. And what happened, you can see, is my moment vector R, my moment arm R, and my force vector F are both in the XY plane as we've set it up. Okay. So probably everybody just assumed that, but let's just, if we go ahead and see what that looks like, here's X, here's Y. Okay. Z is going to be coming straight out of your screen. That's positive Z. Now, what we have found is negative, that the moment's in the negative direction. So if you take your hand and you curl it around like that, so R crossed with F, okay, and then your thumb is going to point towards in the direction of the moment, okay. Now, my camera is reversing some things. So for me to do the right hand rule, I've got to use my left hand and I got to be real careful with all of that stuff. But anyway, it'll work better for you. Just, R, F, boom, there you go. Okay. And eventually you're going to get where you just kind of curl those things together, boop, and it'll be very natural for you, but it'll take a little bit of practice. Okay. The vast majority of the problems that we're going to do are actually two-dimensional, which this is really a two-dimensional problem. So instead of saying that the moment is minus 460 k hat, we could say it's minus 460. Just call it that. And what we mean by that is that it's actually a clockwise moment. And if you look at the picture, that makes a lot of sense because you can imagine that that force pushing that way is going to try and rotate it down and around. Okay. If it could flex or if it could pivot at O, boop, you see that L-shaped piece would want to move in the direction that's clockwise there. Okay. Now, the point of application is important for getting the amount of that twisting effort. If we had put O somewhere else, if we said, well, what if what about this point right here? We would get a completely different number because then I'd have a completely different R vector. Okay. So you got to pay attention to that. What are they talking about? Sometimes they'll be interested in the moment about the origin, like they did here. Other times it'll be somewhere else. So pay close attention to all that. Okay, so there's the first method. That method is really a sledgehammer. It's not going to go wrong. It's going to work for you every time. What's long about that is you got to do that determinate method. Unless your calculator has matrix and vector functions, in which case you can just define R, define F, do R cross F. Click on your calculator and it'll pop the answer right out. Okay. In fact, that's what I did. Okay. You could use Wolfram Alpha, like I showed you. The calculator I like to use is Calculator Infinity. It will do it also. I'm sure that many of you have calculators that will do this, and that's fine with me. You do not have to do these by hand. Um, you should know how to do them by hand, okay? But I'm not going to force you to do that, okay? Um, all right. So let's get to the second way of handling these situations. The second way to handle these situations is to realize that we could just talk about magnitude. And in terms of magnitude, a cross product is the two vectors times the sine of the angle between them. So that would be this angle right here. There's my angle theta. Okay. So we know that R, we could find the magnitude for R, we could find the magnitude for F. I'm not going to go through that. I mean, that's super simple. But I'm not going to go through with this second method completely because we don't know theta. All right. And finding theta is going to be a whole thing all by itself. Okay. Not hard to do, but it's a whole thing all by itself. All right. All I want you to see here is that if we had theta, and in a different problem, it might say it makes an angle of 27 degrees. Fine. Great. You use 27 degrees, you're good to go. The only thing we got to watch out for is it going to be clockwise or counterclockwise? Because then we'll want to put positive or negative. Okay. Okay. The one thing I do want to talk about with this is I need to introduce for you an idea called the line of action. So our force, anytime we've got a force, it's going to act in a particular direction at a particular point in space. Okay. And that line of action is important when it comes to your moments because the moment arm depends on the distance between our point of interest and the line of action. Okay, so see how I've got a triangle right there? Okay, guess what um, F, or I guess we want to look at here, R sine theta. Okay, so pause the video for just a second and figure out what is the distance R sine theta. Okay, so pause that. I'll wait. Okay, did you figure it out? R sine theta is actually the black line that I drew. Okay, so we're really saying we want to take the magnitude of the force times the distance of closest approach to the line of action. So if we had the distance of closest approach to the line of action, we could just use that. Okay. Now, in this particular case, that's not any fun. Again, that's a whole thing unto itself. But there might be some other case where the shortest distance to the line of action, or the perpendicular distance to the line of action, that might be easy to identify. And if it is, we can just use it. We would just say this is going to be 100 times whatever that happens to be. Okay. And then we're going to have our answer. It's just that in this particular case, that's a little bit yucky. So it's not a great way to go. But there is something informative there, because realize that I can use the pink line, the real moment arm, and modify it times sine theta, or I could use that shortest distance, the black line there, but I could put some other line in here, okay, this line here. And if I want to know, well, what's the moment along that moment arm, it's going to be the same, because it goes from the origin out to the line of action. I could do it over here. I could say, well, what's that moment going to be? Well, it's going to be the same, because it goes from the same point of interest out to the line of action. I could come out here. Same thing. I could come all the way up here to the intersection. Same thing. Okay. So our moment is determined by geometry. Where's the line of action? Okay. And what moment arm are we going to be using? All right. But we've got a lot of flexibility within those parameters. Okay. So let me erase some things, clear some of this up. I actually want to get rid of the blue things there. I'm going to get rid of this guy. I'm going to get rid of that guy too. Okay. So, because now we're going to get into the third way to approach this problem. All right. And you know what? Actually, I should just get rid of a few other things too. Oh, there we go. That'll work pretty nicely. One more. Nice. It cleaned up well. All right. So the first way was the sledgehammer. So the first way we could go about this is we just define RF and crank it out in a cross product. The second way is we could think about magnitude. So if we knew the angle between our two vectors, we could get it. Okay. Now here's the third way. And this is really powerful. Okay. The third way is we take our vector and we split it into components. All right. So let me call this Fy. And we know that Fy is it's negative 60. We've already figured that out. And then here's an Fx. Just like this. Okay. Now let's take a look at R, and let's try to do something similar with R. So in other words, I've got an Rx here. There's Rx. And I've got an Ry, which I can put here. Just like that. Now, what's the line of action of Fx? The line of action for Fx is this right here. Look at this. Just like that. So if I want to know the moment only from Fx, I can use Ry. So I could take Ry and combine it with Fx. And that would be the moment from Fx. Okay. And in this particular case, that would happen to be a clockwise effect. Okay. So Fx is this way, Ry is up. It's trying to kind of make it go like this here. Okay. But we could do the same thing with Fy, right? Here's my line of action for Fy, and it's perpendicular to Rx. So that means I've got this too, Fy Rx. So what we're doing in this third method is we're going to break up the moment into moment generated by the X component and moment generated by the Y component. And then we put them together. Okay. And so my moment, I'm going to put these things together just like this. Okay. But I also have to keep track of which one's clockwise, which one's counterclockwise. Are they both clockwise? Are they both counterclockwise? I gotta sort all that out. If they are clockwise, I gotta call them negative. Okay, so let's start with Ry and Fx. Well, that's going to be negative. We already figured that out. Ry is 2, so we got minus 2. And Fx is 80. Then we're going to get the other part. And I wrote it in reverse order there. Sorry for, I hope that's not confusing. There's the 80 for Fy. And Rx is 5. Uh-oh, some of you caught that. I know you did. If we were sitting around in class, some of you guys have been like, wait a minute. Because that guy is 60. There we go. Okay. I was running the numbers on that in my head, and I was like, that's not going to work out. So I was like, I've screwed up somewhere. Anyway, what we're going to get is minus 460. Okay. Now, I do want to show you real quick before we end this how this K term that I have right here is exactly the same as this. Okay. So the third method, really, one way to think about that is to say we're only doing the very last part of our determinate. Okay. That's one way to think about it. The easier way to think about it is to go, oh, what moment does my Fy give me? What moment does my Fx give me? Are they clockwise? Are they counterclockwise? And then I combine them appropriately. Okay. So there might be other times where one of them is clockwise and the other one is counterclockwise. Then I'm going to have to subtract. Okay. And I think we're going to end up doing some examples of that pretty soon. But there's your big overview. Okay. So we can go sledgehammer, where we simply take the cross product. We could look at the magnitudes, deal with r sine theta, or we can split our force into components, find the moment from each one of those.